Welcome to the channel. Today I'd like to read with you and show you and maybe together go over one of my favorite blog posts or articles about machine learning. This is from 2015, before I had much exposure to machine learning. And I remember reading this article and it really sort of, sparking something in me. I love it as an example of just communicating complex concepts in machine learning to a technical audience. This is, of course, the classic blog post by Andrej Karpathy titled "The Unreasonable Effectiveness of Recurrent Neural Networks" from May 2015. The opening words are, there's something magical about recurrent neural networks. I still remember when I trained my first recurrent neural network for image captioning. That is true, and that is still the case. And I think it's generally the case with machine learning. When you see models that generate text, there's always, I cannot get used to it. It's been 5 years now of me looking at it, from these early sort of RNNs until GPT models, and it keeps being more and more interesting. And this is one of the first times that I was exposed to it, and I believe the author here made a really great presentation, I think, that made it accessible. And I think a lot of people in academia around that time have played with RNNs. But then this is one of the times or artifacts of communication, I guess, this blog post that made it available to a wider audience that was not typically, reading machine learning papers. And so this is an opening article and a link to a GitHub to train character level language models based on LSTMs. So these are models that you feed them a bunch of text that you train them on, and they generate more text. But unlike, let's say, some of the more recent models, these are character based. So they output one letter at a time, one character at a time. So, letters and spaces, they do it one at a time instead of one token or one word at a time. And they're interesting in their own way. I like the structure of the article, and then you have these sort of academic paragraph titles, your sequences, just ways to break down the various paragraphs. And this, I believe, is a classic image that really sort of shows you how versatile RNNs were, that you're able to feed them one output or work with one time step and have one output, so 1-to-1. Or you can have one input and multiple sort of outputs, one at each of the 3 time steps. And I think that there are good examples we can give to a bunch of these. So I think so this would be just a regular sort of neural network. This is maybe something like image captioning, where you'd put the vector that you get from a CNN, maybe co-trained with this RNN, and then the model would output a series of words or characters or letters to write the caption to the image. Many to one, this is where you have a lot of text going in and then one output towards the end. I think a good example of this is sentiment analysis. So if you feed a whole maybe review from Amazon and you want you've trained the model to say, is this review saying positive things or negative things? So this is a way to feed all of that data in sequentially into the model, but only get the output towards the end. Many to many, this is what's called sequence to sequence. So this is the type of models that are machine. I think, okay, so there are examples here. So sentiment analysis, Many-to-many or sequence-sequence is machine translation. I think that's the canonical example. But you can also think about, GPT-3 is many-to-many. You give it a prompt and it outputs. But it's not an RNN, it's a transformer. But it's under this umbrella of models that take a sequence of text and output a sequence of outputs. This is a synced sequence video classification, where it's each frame of video. I can't think of coming across models like this myself, but I really love this figure and sort of how it communicated the idea. Another glance, very visual on using sequential processing. So even in images, how RNNs or processing in sequences can be helpful. I didn't program a lot in Python by 2015, but I really liked this syntax. I thought it was simple. I don't recall that I really understood a lot of what's happening here. I didn't know what 10H is or NumPy. Would have wanted the variable names to be a little longer, and so I would have maybe called this hidden state. Just as a newbie, I think that was, but including it it gives you a little bit of, it's kind of reassuring, and I've grown to sort of understand that most articles I'm not going to understand 100% of them when I read them, or maybe 80%, or maybe the majority of them. But they give you some exposure that maybe if you read them again, maybe if you read the second or third or fourth article, that knowledge sort of collects itself and you learn a little bit more. So an explanation on character level. So this is an explanation on embeddings. So this is a visualization for how embeddings are done. And this is showing the input vectors and output vectors, and how the RNN would process each character. I don't know if they have a dimension. Okay, so this is 4 dimensions in the example here, but I think the code would probably be something else. And then this is how it was trained. And then here it gets really fun. So fun with RNNs. This section is very impressive. This is where he starts feeding chunks of text to models, and the models start to generate text in interesting styles. So the first example is Paul Graham, who's the founder of Y Combinator, has a lot of excellent essays on starting companies and startups and fundraising and building companies and technology as a whole. So he has a lot of essays out there. So this first model was trained to generate, and then he starts showing examples of the text that the model generated. So this example says, the surprised investors weren't going to raise money. I'm not the company with the time. They are all interesting quickly. Don't have to get off to the same programmers. There's a super angel round fundraising. Why do you call do? If you have different physical investment, are become in people who reduced in. So it's fascinating because it's broken, but it's broken in a very interesting way. So you can see that there are words and sentences and technical terms and programming and startup and entrepreneurship terms, but it's not just randomly generated. It has some level of randomness, but it learned something from just, it saw some patterns in what was in the data that it was trained on. Fast forward 4 years later, and we have GPT-2, which solves this basically, and can output text that is very comprehensible, but without, and GPT-3, which takes it a level further, but without communicative intent. So there isn't kind of a soul or intention behind that yet. We haven't really figured out how to do that. But through the statistics that the model finds in the patterns and that it finds in the text, it can model text that looks more and more interesting. And then an idea about temperature and how that goes in calculating which character to pick at each time. Shakespeare examples. This was interesting. Wikipedia, but this is not only text, but text with the, markup or code that goes into linking Wikipedia articles. This was fascinating. There's code here. Okay, so there's LaTeX with code, and we've seen GPT-3 work on some mathematics recently, and I think it sort of proved something. I mean, they filed one of its proofs as something that the model created originally. So 5 years from this article, I think this took off in a bigger way. Source code, this was also very interesting. So he collected a lot of the Linux, he concatenated a lot of the Linux repository on GitHub. So that's 500 megabytes of C code, and trained models to generate C code. So these are some of the examples. He also, this is another great section where it shows the evolution of samples while training. So the examples we saw above is take some, a lot of text, throw it at a model, and then after the model is trained, have it output some text. But here, the idea is that, okay, let's stop it in the middle of training and say, okay, model, generate some text now. And this first example is after 100 iterations. And you can see that the words are all nonsense. And then after, 300 iterations, you can start to see some sort of form coming in, that there are 3 to 5 or 10 letter words, all separated by space. There's a sense of punctuation that started coming in. There's a period here, a comma here, and then a space after each of them. There's a quotation that was opened and then closed. So the model is now, at 300 iterations, it started picking up some ideas of syntax and punctuation, at least. But the words, some of the simple words, the model is starting to pick up, in, on. So these are started being modeled. It becomes more and more comprehensible the more the model is trained. So this is at 500 iterations. You can say see his, but it's still a lot of gibberish. At 700, it starts to become a little bit more English. So this is all trained on Leo Tolstoy's War and Peace. And towards the end, you start to see it's properly spelled words. Why do what that day? Replied Natasha, with quotations and commas, and wishing to himself the fact that Princess Mary was easier. So this is pretty fascinating. And then it ends with a couple of visualizations and links to articles. And the visualizations do a couple of different things. This first row here is text that we are giving to the model. So you pass the model the letter H and maybe the letter T. And then the 5 columns under it is the highest predicted characters that the model is predicting that would be the next letter. And so we're not really taking any of the output of the model. We're just seeing the probabilities that it's expecting based on the input text, but we're not feeding that input back into the model. We're using it just to create this plot, and we continue feeding this input text. So with the color coding, there are a couple of different things that are happening here. I think the more important one here is how red or white this color is. And so what you see here is that when the model sees a URL, because it's seen a lot of HTTP : / it has seen a lot of that, so it can predict that, with a very high likelihood, if I've seen HTTP, then the next character would be a colon, and then when it does get the colon, the next one would be a /. And so this is what's happening here. So input is T, and then the model predicts with a very high accurate probability that the next character is T. Now we give it the next T, and it says with a high probability the next character is a P, and then that goes on. And so after the www dot, you start to see the probabilities get diffused a little bit. The model is not very sure about what character comes next. So you see all of these characters, B, A, S, N, all have some level of probability of the model picking them. So it's not really sure. And that continues for a while. Until when we see new, it starts becoming, the model is like, okay, I've seen this NEW, and a lot of the times it's followed by an S. And so maybe it's news, and so it assigns S a high probability, and then a dot, and then after the period, it's like, okay, is this .com? Is this .org? So you're only looking at one cell. You're not looking at the ones next to it. You're looking at this one here. So after the period, what's going to be the top level domain, I guess? So most likely it's C. What is E? I'm not sure. EDU? And then O would be org. What is G? I'm not sure what .g would be, but N is probably there for .net. And then, so when it sees the C, it's like, okay, I know this. I've seen. After the C usually is an O, and then an M, and then a /, and then it's the probability starts becoming diffuse. It's not sure again. So this is the first component of this, is the bottom 5, let's say, rows. And this goes on with a few more examples here. Now, the second component here is these blue and green for the input tokens. And I think this needs a little bit of setup to understand. But what the author is doing here is an extension of work that really goes into a little bit deeper in this second visualization. Which is the idea here is that he's picked specific neurons and is projecting the value firing of those neurons. It's blue-green based on the firing of a randomly chosen neuron in the hidden representation of the RNN. So green is very excited and blue is not very excited. So what you can tell is that, or I really probably mentioned this, is that they've looked at a lot of different neurons and picked a few that could be interesting. And so you can see that this one is excited by focusing on the domains. Let me look back at the... So this would be visualizing the value of the neuron post the activation, right? And what activation are they using here? Would it be a 10H? The hidden state is this is the activation function, and plus NP. The output vector would be the dot product of the two. Because I'll show you something here. And we'll get to this after the final visualization. So this goes a little bit more into looking at specific and certain neurons. And this is a very fascinating part of this. So from the author's examinations and looking at so many different RNNs, he's picked out a few that exhibit some interesting behavior. Like this neuron that has, high firing when it's at the beginning of, or let's say, okay, it calls it sensitive to position in line. So towards the end of the position, it's firing of a line, it's firing shifts. And this one that turns on inside quotes, and this one that activates inside if statements. So I've always thought, and the majority would be kind of like this. It's very hard to interpret. And so this is one of the early visual ways of trying to understand or interpret what's happening inside of a trained neural network. And there's extensions to this interpretability work, and I've been exploring the space myself recently as well, and trying to actually downloaded this code months ago. This is one thing that sort of I did not understand, or it wasn't clear to me when I first saw this, is that this says PCA. I'm not sure that the neuron firings are the result of the activation function, whether it's tanh or something else. So what I want to show you is this again here, PCA. So this is the value that the rendering here is showing. So this variable is called PCA. So when I saw this, and I still wonder, are these actually specific neurons? So if you train a model with, let's say, 300 units, are these the outputs of one of the 300 units? Or is this a dimensionality reduction of sort, that you fed activation vectors of the 300 neurons into PCA, and PCA shrunk it down into, let's say, 20 or 30 different neurons, and that's what we're showing here. So I'm curious if you know, or if you've seen, or if there are any hints in this code base that you've came across that indicates that, beyond, I think, the name of the file and the name of the variable. Please let me know. And for me, this stuck with me, honestly. And this, when I started to give a lot more of my own time towards interpretability and machine learning and trying to understand these, GPT models specifically, I was like, nobody really has done this to my knowledge with transformers. In a very visual way, so that's why I sort of wrote my penultimate, is that the word, blog post here that sort of grew out from that. So where I have a GPT-2 model, I give it this input, and it generates this output, and then this shows you saliency. So this is not neuron activations, but this is neuron activations. But it's not showing you direct neurons because I've looked at that. I've drawn giant heat maps of 3,000 neuron layers of transformers versus 200 tokens. And they're very noisy and hard to interpret and very sparse. So a lot of them do not fire the majority of the time. But then there are dimensionality reduction techniques like NMF, non-negative matrix factorization, that can take 3,000 or 18,000 neuron activations and shrink them down to, let's say, 4. And those would show you interesting results, kind of like this. So these are 4 patterns that underlie, let's say, this GPT-2 model. So a bunch of the neurons fire when they see the first token. A bunch of them here fire whenever they see a number. A bunch of them fire when they see a name. And so that's just a toy example. But it's all sort of on this explanation, on this path of really being fascinated and interested in what's going on inside these models and trying to look deeper and try to grasp meaning. And one of the major articles that took this to And so this is an area of debate in machine learning. So the sentiment neuron is one notable, there's an O missing there. This is one notable work from OpenAI where they've done this. I think this is still as LSTMs, there's still RNNs, trained on sentiment, and then from that they've discovered, let's say, a neuron whose value correlates with the sentiment of the text. And another example here, and I think this sort of draws from the visualizations from that Karpathy article. So these are the firings of this neuron. So it's the characters are beautifully developed, interactions are exciting, complex. So this is all positive. So the model or this neuron is firing towards the positive. But then when this says maybe the absolute worst disparity in quality between novel and screen adaptation, you can see it turns red, or the value sort of flips. Now, while this is interesting, there has been debate. So this is not just all clear cut. So there has been ways in which people are saying, yes, there could be neurons that fire in response to input like this. But if your model is actually generating a prediction for sentiment, then maybe these neurons don't necessarily contribute to that output of the model. So that's one area of nuance that is often raised in these discussions, and more there are these ideas about interpretability methods have to be a little bit more falsifiable, have to make claims that can be falsifiable. So more and more we're trying to be a little bit more, the field, the community as a whole is trying to find ways that, how can we be a little bit more scientific? How can we make assumptions or claims that can be verified or falsified when we're talking about interpretability? So I'd like to talk more about interpretability and explainability in the channel in the future. But then this is one of the areas that really sparked it for me, this post, and sort of looking at specific neurons and saying, maybe if we looked closely enough or shrunk dimensionality in certain ways, we can really understand it. So there's source code here and some discussions at the bottom. So this is a classic. I go back to it every now and then. I just love it from a technical writing point of view, but also machine learning and sort of communication. So there is a talk and there's a paper, and this is a blog post that expands on that. And I don't think we in machine learning have enough of this sort of communication, broad communication of these topics to people who are not completely caught up with the literature, who can really welcome new people to the field or to the topic. So that's very grateful to Andre for this, and for everybody who tries to write and create videos and explain these concepts to wider audiences. Thank you for watching. If you've experimenting with new formats here, I hope you enjoy it. We'll be back with more articles and other kinds of videos in the future. So if you've enjoyed it, please let me know. You know how to subscribe and like and maybe comment, or let me know what you think, or if you have other articles that you think have moved the needle for how you learn machine learning or topics in machine learning. Let me know. I'd be happy to take a look at them. Take care.